Hello. In this video, we're going to talk a little bit more about heat transfer. So we can actually write an equation for the relationship between the amount of heat that's transferred to or from an object and the temperature change that the object experiences during that heat transfer. So we have that equation down below where heat is equal to m times c times delta T. So what do those all stand for? So m is the mass of the object that we're interested in, and then c is something called a specific heat for that object. And we'll talk about what that is in a second. And then delta T is the change in temperature of the system that we're analyzing. So we can break this down as the final temperature of the system minus its initial temperature. So we can actually rewrite this equation to be a little more detailed. So this is equal to mass times specific heat times the final temperature minus the initial temperature. Thought I flipped it for a second. Okay, so let's say, for example, we're looking at a copper penny and we heat it up. So if we know the mass of the penny, or the copper part of the penny, and we know its specific heat as well as the initial temperature and final temperature of that penny, then we can actually calculate the amount of heat that was transferred to the penny from, let's say, a flame. Now let's talk about what specific heat is. So this is going to be a constant for different substances. So every substance has a specific heat value. This is kind of similar to density. Every substance has a density, right? And this is going to be reported in units of lowercase calories over grams times degrees Celsius, or you could use Kelvin. So you could use either temperature scale, degrees Celsius or Kelvin. Now the temperature that's used in the table down below, the scale that's used is degrees Celsius, but we could easily convert that now that we know the conversion between degrees Celsius and Kelvin. All right, so let's look at some of these substances. So it looks like we have aluminum, and that has a specific heat value of 0.215 calories per 1 gram and 1 degree Celsius. So I'm just going to rewrite this up above. .215 calories over 1 gram times 1 degree Celsius. So what does that even mean? Well, it means that if we have 1 gram of aluminum and we want to raise its temperature by 1 degree Celsius, we have to provide 0.215 calories of energy. So that could be in the form of heat, right? All right, so keeping that in mind, we can look at some of these other substances down below. So let's look at copper. So aluminum and copper are both metals, and they have pretty low specific heat values. Copper's value is 0.092. And then let's find some other metals. We have iron. Iron's specific heat is 0.108. And it looks like that's it. So metals, if we think about heating them up, metals heat really quickly, right? They absorb heat very easily. So it doesn't take very much energy for the temperature to spike for a metal, right? However, if we look at other substances, like let's look at water, for example, you probably know from experience if you try to heat up water, it takes forever. A watched pot never boils, right? And its specific heat value is 1. So that is much more energy that we need to provide in order to increase the temperature of water. So again, for water, I'll just write it off to the side. Its specific heat is 1 calorie over 1 gram times 1 degree Celsius. So again, to heat up 1 gram of water by 1 degree Celsius, we have to provide 1 calorie of energy versus aluminum, which only needed 0.215 calories. All right, and then if we look at some of these other substances, let's look at hydrogen, which remember is a gas. It takes 3.4 calories of energy to increase the temperature of hydrogen gas by 1 degree Celsius. So that's a lot of energy that is needed to heat up a gas. So just keep that in mind as we kind of go through this. So in general, if you have a higher specific heat, that means it's more difficult to heat that substance. But if you have a lower specific heat, then it's easier to heat. Okay, so let's look at an example of how to use that equation we saw on the last slide. So this question asks, what quantity of heat is transferred when a 150 gram block of iron metal is heated from 25 degrees Celsius to 73.3 degrees Celsius? And what is the direction of heat flow? All right, so we're given a lot of information here. So we're told that the mass of the iron block is 150 grams. And then we're also given temperatures. So it looks like our starting temperature is 25 degrees Celsius. So T initial is 25. And then T final would be 73.3 degrees Celsius. Okay, and if we write out the equation for heat that we saw earlier, so mass times specific heat times change in temperature, it looks like the only thing we're missing is that specific heat, C. So let's find that on our table on the last slide. So iron has a specific heat of 0.108. Okay, so let's write that down. All right. So let's plug all of this into our equation. So the amount of heat that's transferred is equal to the mass, 150 grams, times the specific heat, 0.108 calories per gram and degree Celsius. And then our change in temperature, remember, is T final minus T initial. Let's see if I can squeeze that in here. Okay, I just barely squeezed that in. All right, so let's take the difference in temperature first. So I'm just going to rewrite this. All right, so we've got, let's see, 73.3 minus 25 gives us 48.3 degrees Celsius. All right. So let's cancel some units. Now we know that heat is going to have a unit of calories, but let's just make sure we set everything up correctly. So it looks like grams will cancel because we have the unit in the numerator and the denominator. And then degrees Celsius will cancel as well. So we're left with calories, which is perfect. And now all we have to do is multiply 150 times 0.108 times 48.3. And it looks like we have 3 sig figs for everything. Well, our first value, the mass has 4 sig figs, but our specific heat value has 3, and our temperature difference has 3 sig figs. So we'll stick with 3 sig figs for our final answer. So we get 782 calories according to our calculator. Now, where did heat flow? Did it flow into the metal block or out of the metal block? So it looks like the temperature increased, so that would tell us that heat flowed into the metal block. Okay. Now, that brings up an important point about this equation that we learned. The direction of heat flow is not shown in our equation, so it might be difficult to tell if heat is flowing into the object or out of the object, unless we're given specific information. Now, if energy does go into an object, then that tells us the total energy is going to increase, right? We're heating something up, so the energy increases. So that should mean that the values of heat and our change in temperature are positive. But let's say energy is coming out of an object. So that would mean that the energy of the object is decreasing, and the values of heat and delta T are negative. So that is one way that we'll be able to determine if heat flowed into an object or out of an object. So if we have positive values of heat and delta T, then that means energy went into the object. But if the values of heat and delta T are negative, then energy is coming out of the object. So, for example, let's say that we're told the initial temperature of an object is 50 degrees Celsius, and its final temperature is 10 degrees Celsius. So, according to our delta T, T final minus T initial would equal 10 degrees Celsius minus 50 degrees Celsius. And that gives us negative 40 degrees Celsius. Now we can also tell, given the initial and final temperatures of this object, that the temperature has decreased, right? So that's going to give us a negative difference in temperature, and we know that heat flowed out of the object. So energy flowed out of the object. Okay, let's do another problem. Let's say we have a 10.3 gram sample of a reddish brown metal, and that metal gave off 71.7 calories of heat as its temperature decreased from 97.5 degrees Celsius to 22 degrees Celsius. What is the specific heat of the metal? And can you identify the metal from the data on the previous slide? So from the table that we saw earlier. All right, so it looks like what we're trying to identify is the specific heat, or C. Okay, so let's write down what we were given. So we were given the mass, which is 10.3 grams. And then we were told that the heat is, let's see, so that was given off of the object. So we lost heat. So we want to make sure that's a negative value. So that would be negative 71.7 calories. And then the temperature decreased from 97.5, so that's T initial. And then T final is 22 degrees Celsius. And then again, the equation we're using is the one we saw earlier. And we want to solve for C. That's what we're interested in. All right, so plug in those values and rearrange the equation to solve for C. And while you're doing that, pause the video. And then once you're done, we'll compare our answers. Okay, so let's plug in our values here. So we have, let's see, I'm going to use a different color. We have negative 71.7 calories is equal to 10.3 grams times C times, let's see, we want to do T final minus T initial. So 22 minus 97.5 degrees Celsius. Okay, so let's see. Let's figure out what our temperature difference is. So I'm going to rewrite my equation here. So 22 minus 97.5. We should get a value of negative 75.5 degrees Celsius. All right, now how do we isolate C? How do we move our other numbers over to the left side of our equation? Well, we can divide both sides by 10.3 and negative 75.5. So C will equal negative 71.7 calories divided by 10.3 grams times negative 75.5 degrees Celsius. Oh, and actually I'm just going to move my equals sign over a little bit. There we go. All right, so luckily our negative signs are going to cancel. So we'll get a positive value, which is good because specific heats are never negative. And then also our units don't cancel, but that's actually okay in this case because the units for specific heat are calories over grams times degrees Celsius. So what we're going to do is just take 71.7 and divide it by 10.3 as well as 75.5. And the value that I got was 0.0922 calories over grams times degrees Celsius. Okay, so that's our specific heat of our metal. So let's go back to our table and try to figure out what the metal is based on this value. So I'm going to go back a few slides here. All right, so looking through the table, the specific heat value that matches is copper, 0.092. And that makes sense given the problem because we were told we had a reddish brown metal. So this would be copper. All right. So I think we'll stop there for this video. In the next video, we're going to talk about some terms that we can use to describe the exchange of heat. We're also going to talk about phase diagrams. So I will see you then.